Ahaan is one of them. He's a candidate master on Codeforces and an ICPC regionalist. And one of the quickest to have become candidate master in my college. That is only around 200 problems. So yeah, I think this lecture will be very informational to you. Over to you.
Hello guys, I'm audible right at the back. Yeah, so I'm Ahaan, and I'll be taking this lecture on graphs and trees. How many first yearites do we have? And how many second yearites? It's almost 8. Alright. So I'll be starting right from the basics. So even if yeah, so I'll be starting right from the basics. Even if you don't have any idea of graph theory, it's alright. Fine, I'll start. So that's a basic outline of what I'll be covering. In between, we'll have some questions, and so we'll be discussing some questions in between, and that should be helpful. I hope that's helpful to most of you. Fine. So first, an introduction of graph theory. So what's a graph? We have a set of nodes, and we connect them using a set of edges. Together they form a graph. Alright? The next important part is graph traversal. So if you are given a graph, you need to be able to navigate through the nodes of the graph via the edges. And that's what I mean by graph traversal. So there are two main algorithms for graph traversal: depth first search (DFS) and breadth first search (BFS). I'll start with depth first search. So we randomly pick a node. I can now go to any node that is connected to the highlighted node. So let's say I go to node 2 here. I could also choose node 3. If I keep repeating this step, so from 2 I go to 4, from 4 I go to 6. At 6, I do not have any uncovered node left that's in contact with 6. So I go back to 4. At 4, I do not find any uncovered node as its neighbor. I go back to 2. I go back to 1. Now when I'm at 1, again I have 3 which is uncovered, so I go to 3. And then I move to node 5. In this manner, I have covered the whole graph. Any questions there? How many of you are acquainted with such graph traversal algorithms? Okay, so for you guys here, was it clear? Not clear? Alright, I'll go through it. So I randomly pick up a node. Right. My objective is to be able to go through all nodes that are connected in this graph. And I can only go by the edges. So as I'm at node 1, so I pick up any edge from node 1 and I take that edge. So in this instance, I take the edge between 1 and 2 and I go to node 2. Right. Then from node 2, I go to node 4. I don't want to go back to node 1 because I've already discovered that node. So I move to node 4. From node 4, I move to node 6. All I'm doing is moving along the edges of the graph, that's all. At node 6, I'm not left with any edge that leads me to... sorry?
It's very understood this part.
That's okay, right?
That's fine.
Okay. So essentially this is what we do in DFS, and we go through all nodes that are connected to the first node. Alright, the next algorithm is BFS, breadth first search. So here in the ith step, I will be reaching nodes at distance I from my source node. So initially I'm at my source node, 1 in this case, which is at distance 0 from itself. Next I move to all nodes at distance 1. So nodes 2 and 3 are at distance 1 from the source node. So I go to those two nodes. You could also see how I've implemented this. So I initialize a queue, right? So for those of you that don't know what a queue is, it's a simple, you could just take it as a list. It's just a list to which I can append at the back, and I can even remove nodes from the front. So I had a queue initialized with node 1. It's connected to node 2 and node 3. So clearly they are at distance 1 from node 1. So I add those to the queue. Next I move to these two nodes. They are connected with nodes 4 and 5. So clearly those nodes are at distance 2. Next I move to these two nodes. Now node 5 is not connected to any new node. So that portion will terminate. And node 4 is connected to node 6. So I'll add that to the queue, and in the next step I'll move to node 6. In this manner, I'm going through all the nodes. However, here the order in which I'm going to the nodes is in order of their distance from the source node. Right. So again, the whole graph is covered, and in this manner, I also got the distance of each node from the source. Is everything clear until now? Any issues?
In the previous
Yeah.
Step between 1 and 4, can you talk about
Yes.
1 and 4?
yes, 1 and
Okay, sorry. So there was an issue with the. Fine. The graph that we saw till now, all nodes were connected to each other via some path. We always had a way to go from node I to node J, right? But if we look at this graph, there's no way to go from node 1 to node 7. Essentially, we have two sets of nodes, first being 1 to 6, and the second being 7 to 9. And they are both independent in the sense that there's no edge connecting a node from the first set to the second set. So if I start moving from any node in the first set, I would only remain in the first set and I won't be able to move out of it. So these are called different components of a graph, different connected components of a graph. So in this example, we have two connected components. So we could again find the number of connected components by graph traversal. So if I start any graph traversal algorithm from node 1, then I would be able to cover all these nodes. After that, if I start graph traversal from node 7, let's say, then I would also be able to cover all nodes in the second set. I would also be able to find other things such as which nodes are present in the first component, which nodes are present in the second component, what are the number of components, all related things I will be able to find. Alright? And so we are good to go forward? Good. Next, I will be dealing with trees. So trees are just a special type of graphs. The first property is that there are no cycles in it. And secondly, they must have only one connected component. All nodes of the tree must be connected via some path. If they are just acyclic and they are not connected to each other, then we basically have a group of trees and they are said to form a forest. So coming back to a tree, they are just a set of connected nodes without any cycles. I haven't formally defined what a cycle is, but I guess intuitively it should be clear what's meant by cycle. So if such a graph has n vertices, then it must contain n minus 1 edges. Alright. We now come to rooted trees. So a tree by itself does not have a root. A tree is just, as I said before, a set of n vertices that is connected and acyclic. However, we can assign any node of the tree to be its root. So, for example, even in this graph, I have highlighted 1 to be the root of the tree, but I could have even made, for example, node 6 to be the root of the tree. It may appear here that I've placed 1 right at the top, so 1 must be the root. But even if I call 6 to be the root, I can similarly draw a diagram in similar form. Right, so the root of the tree is something that we define. Yeah. And once we define what is the root of the tree, we each node also has a parent. So basically, if we move from a node to the root, the node that's directly above is called the parent of that node. Secondly, there is only one simple path from a node to the root. Or in fact, between any two nodes, we only have one simple path. Okay. So we now have a question. You are given a rooted. Okay. Was everything clear until now? So I have defined what's a tree, and I had earlier gone through the various graph traversal algorithms. So you're able to navigate through the nodes of the graph and do whatever you wish. Secondly, you know what's meant by it. Fine. So we have a question now. You're given a rooted tree with n nodes. Each node I has a value ai. You may perform the following operation any number of times. We choose any node of the tree and we remove the whole subtree corresponding to the node. So what's the subtree? In this example, if I look at the node 2, the set of nodes 2, 4 and 5 form a subtree. So I can pick any node and remove the whole subtree corresponding to it. After all these operations, I need to maximize my profit. The profit is defined as the sum of the values of all nodes which are in the tree minus x times k, where x is some constant greater than 0 and k is the number of times I have removed a subtree. So I need to maximize this quantity after all the removal operations that I have performed. You could take some time and think on this problem. We'll probably discuss it in around maybe 2 minutes. Has everyone understood the problem?
Is there any constraints
Constraints on?
X or the number of nodes?
So x is greater than 0, you can remove any number of nodes. explicitly mentioned it, but AI can also be negative. If all AIs are positive, then there won't be any point in it.
prefix tree बनाएगा DP of x का k मतलब तू अभी तक k ऑपरेशंस किया और मैक्सिमम कॉस्ट ऑफ t
Alright, so any clues? Anyone? You needn't have found the complete answer, but anything you were able to figure out that.
See the nodes, like you can start with the nodes which are connected with the least and the smallest subtree and see if their net value is negative. So we will start removing them and then we will go upwards.
Yeah. Okay. Fine. So whenever you are presented with such a problem, the first thing you need to try to figure out is when would it be beneficial to remove a node and when not. Right. So okay. For example, in this tree, if I remove the subtree corresponding to 2, then the decrease, rather the change in profit would be because of one extra operation we'll be losing out on x, and because we're removing the subtree minus the value of the subtree. So intuitively it seems that whenever the value of a subtree is negative, only then we should try to actually remove it. Another thing we could look at is that, let's say we are removing a node x, right? We are allowed to remove a set of nodes. So let's say I remove a node x. Would it ever be beneficial to remove any node that's a child of x? Okay, so could anyone tell me why not? Sorry?
It would increase the number of operations unnecessarily.
Yeah, it would increase the number of operations and there won't be any change in the value of the nodes. So, fine. But, okay, in this, so that's how you would start approaching a problem. However, in this particular case, we won't really be using it, but yeah. So the way to go about this problem and many other tree problems is by regression. Could you now think what we could do?
प्रॉफिट को डिक्रीज करना है, प्रॉफिट को डिक्रीज क्यों करेंगे? अगर तेरा होल सप्लाई अगर सम जीरो है, सॉरी सम नेगेटिव है, तो तब उसको रिमूव करने से हमारा प्रॉफिट
Yeah, so could anyone think of what we could do?
नॉर्मल अरे ऑफ फैक्टर्स चल जाए,
So, fine.
अरे ऑफ फैक्टर्स
The first thing is that if you figure out an algorithm, make sure you prove its correctness. Right? Otherwise, if you randomly try out things, then essentially in most cases you will be trying out greedy algorithms, right? And they don't always work. So, for example, some people suggested that maybe you choose the moment you get a value that's negative, you remove that subtree. Or something such. So let's just start bottom up and I remove the first value that's negative. Should that work? No, because then I could have other values above it that are negative as well. And we just proved that if I'm removing a node, then there's no point removing another ancestor on top of it. Maybe if you start from the top, it might work if no, again, removing the first negative node isn't of any use because what if that subtree has a positive value, right? So, trying to find out a strategy on your own can be difficult if you just want to, on the basis of the values of the nodes, if you just want to find out which node to remove and which to not. So that's why we are going for recursion. And in recursion, we generally recurse in terms of the value, in this case the profits generated by the chain. So basically I'm not finding an algorithm on my own and I'm just letting my program do all the work. So fine, that's how we solve such three problems in a recursive manner. So let's say I'm sitting at node A, right, any node A. Initially, this would be the root of the tree, and then I would move down. I have a decision too. Right, what are the choices that I have? Sorry? Yeah, so whether I remove the subtree or I keep. Now I need to find the profit generated by each of those choices and take the maximum. Right, if I have to find the profit generated by those choices, of course it's not possible for me to manually calculate it. But I could use recursion here. So how should I write down the profits? Okay, let's say I remove the subtree rooted at it. Then what's the profit of that particular subtree?
Sum of all the
Sorry?
sum of all the values.
If I remove the subtree rooted at it. Yeah, so minus x. I'm not talking about the change I had spoken about in the last slide. I'm talking about the overall profit. So if I remove the subtree, then clearly my profit is minus x. And if I keep the subtree, again, I won't be able to express this directly as a sum of ei and some other values. I'll need to use recursion for this. Fine. So if I'm not removing A, then would A certainly be a part of my tree, my final tree, or no? Right, because the way I'm looking at it, I'm looking at the profit generated by the subtree rooted at it. So if I'm not removing A, there's no ancestor of it that from which I can remove it. So A must be present. Now, what else can I do? Now I need to look at all the remaining nodes. So firstly, is the profit generated by each of those other subtrees independent of each other? Okay. So I have this node A, and it has 3 children. I'm not removing node A. Right. Let's say these children are 1, 2, and 3. I'm not removing node A. So, what can I say about the profit generated by each child as compared to the profit generated by the entire tree as a whole? Sorry?
If you remove a child, the profit will change.
Yes, if we remove a child, the profit will change. But if I look at the profit generated by, say, this subtree, if I call this to be F8, I call this to be F1. Similarly, this is F2, and this is F3. So, okay, so the value of this is basically summation of AI. I'll call the subtree rooted at 1 to be T1, similarly T2 and T3. So this is summation of AI belonging to T1 minus X times K1, where K1 is the number of nodes I have removed in the first subtree. Similarly, I can define F2 and F3. Right, so can't I say that FA should be equal to F1 plus F2 plus F3 plus AI? Fine, I look at both components one by one. Firstly, I look at the nodes remaining. Right, in my profit there are 2 components. First is the sum of values of nodes remaining in the tree. So the sum of nodes remaining in this subtree is equal to, if this is left, then I take this plus the nodes remaining here, and nodes remaining here. So clearly the first component matches. Now I look at the second component, which is K. K is the number of nodes I have removed in the subtree rooted at A, in TA. So the number of nodes I remove here is, if I remove this, then 1, which is clearly 0. So basically it's equal to the number of nodes I remove here, plus the number of nodes I remove here, plus the number of nodes I remove in the third subtree. Right? Not clear? Is it clear? Yes. Okay, so basically I can say that if I remove the subtree rooted at A, then clearly I get a profit of minus X, and if I keep the subtree rooted at A, then I can just sum up the profits of each child, add AI to it, and I get the profit generated by the subtree A. What should I do next? Simply take max for these 2 values. How would I get a profit of A dot child? Exactly. So I'll just keep recursively calling my function, and my program will do the rest. I think it's fairly straightforward to write the base case. So yeah. If you people would have found out the height or the diameter of a tree, then we have used a similar method. The recursive equation is different, but basically we are doing the same thing. How many of you know how to find the height of a tree? Okay, I have diameter of a tree. Okay, fine. So I could even tell you what's the diameter of a tree. So diameter of tree is the distance between the farthest nodes of a tree. So basically, as UV are nodes of the tree, then max out DUV. Okay. Now, if I'm sitting at a particular node, again, let's say A. For now, we'll assume that it only has two children. One and two. Now I need the diameter of the tree, the farthest distance between any two nodes of a tree. So, what would we do? Okay, firstly, how could the longest path look? So, for any path of a tree, it sort of looks like this. We go up, then we go down. If, so let's say U comma B, this is U, this is B. There might be a case if B is an ancestor of U or vice versa, then we just go up. So basically, any path between two nodes of a tree can only take either of these two forms. Either we go up, then we go down, or we just keep going up. So, if I need to find the maximum distance between any two nodes, how should that look? Start from the bottom. Yes. Okay, I think I've defined the diameter incorrectly, right? Does anyone remember how the diameter of a tree is defined?
Find that maximum distance node from that, and then after that you take that node and put the FS on that. You find the maximum.
No, I'm just asking for the definition of that. I think that's the diameter of a graph, probably the maximum distance between any two nodes. Fine. So, okay, I don't exactly remember how it's done, but for how I have defined the diameter of a tree, we could simply take the farthest distance from this node, and then we could yeah, so if we simply take the two farthest nodes from the root, I guess that should work, right? Okay. Okay, no, it need not work. So fine. Yeah. So let's say okay. Let's say I have a graph like this. Okay, is this visible to everyone? This tree? Fine. So what are the nodes farthest from A? Clearly these two nodes. Right, but if I take the distance between these two nodes, it's just two edges. So that won't work. Right. But what I can say is that the distance must be of this form. Unless I have a linear chain. Okay. So let's say this is the tree I'm working on. So the first thing that I propose is that the longest distance should be of this form. Let's say I just keep moving up, then if this is the root, then clearly it has some children here, right? I could just elongate this path and I'll get a longer distance. So this won't be the diameter. So any diameter must first go up, then move down. Okay. Now I look at this point. Let me call this point X. Okay. This could, if this is actually A, then we are correct in saying that I look at the farthest node here, I look at the farthest node here, and I am done. But that need not always be the case. So, okay. Now again, I'll just think of it in a recursive manner. I'm sitting at this node. Okay. So the first option is that if if the longest path is from here to here, then I could just calculate the maximum height here, the maximum height here, and sum it up. Right. So, fine. I'll be taking maps of a few quantities. The first is height of the subtree rooted at 1, h1 plus h2 plus 1. Or the other option is, if this longest path is entirely in the subtree rooted at 1, then I could simply take the diameter of this subtree. So this is either h1 plus h2 plus 1, or I take the diameter of the subtree rooted at 1, and similarly I take the diameter of the subtree rooted at 2. And in this manner I have covered all cases. How many of you are able to understand this? Okay, very few. Fine. Anyone? What issue do you have in this? What part did you not understand? I'll go through it. Fine. So I need to find the diameter of it, the longest distance between any two nodes. Fine. The first option is that for the longest path, I go up here, then I come down. In that case, what would the diameter be? If I go up here, come back down, so if this is, if the furthest I can go down here is h1, and the furthest I can go down here is h2, the heights of both the subtrees, then clearly I would just go as down as I can, go as down as I can, and the diameter is h1 plus h2 plus 2. But in case the longest part does not pass through A, then I simply take the longest path in this subtree, which is the diameter of the subtree rooted at 1. Or I should take the longest path in this subtree, which is the diameter of the subtree rooted at 2. So that's why I take maximum of h1 plus h2 plus 1 or d1 or d2.
सबसे longest BFS यूज करके shortest path.
Okay, so that depends if you are
ये तो बताया था क्यों
calculating the height in terms of number of nodes, then the height of this is h1. Right, I'm taking this
लेमा
node,
से
this
प्रूव
node,
कर सकते हैं
these
कि
nodes.
that longest
Then I'm
is a
taking
part of the
h2 is this node, this node, this node, the diameter
अब
also
उस
of this
node
node is. So
किसी
that's
भी
why I
node
get
के
plus
उससे एक
1.
longest node x आएगा वो x पे वापस BFS लेवल के उसका longest node यही होते हैं.
So that's what I said. If you're taking nodes, it's h1 plus h2 plus 1. If you're taking edges, then it's h1 plus h2 plus 1. Fine, if you're talking, yeah, so it just depends on how you are. Okay, fine, and just because they're all distances, so to keep units constant, I just find the height also in terms of edges and we'll get the distance. Is that fine? height of the subtree and the diameter of the subtree. So even when I'm returning from this function, I also need to return the height of this subtree, which would just be max of h2 comma h1 plus 1. Fine, is that clear for everyone? So the idea was just to show that we can use recursion in a lot of tree problems, where we just write the value of the function in terms of the values of the children, and then we somehow merge them to find the value of the subtree. Yeah. The next thing we'll be looking at is single source shortest path. So the question in hand is basically we are now back to a graph. We are not looking in particular at trees. And we are given a particular node in the graph, say u, and we need to find its shortest distance from all other nodes. And in the particular case where the weights of the graph are non-negative, we can use Dijkstra's algorithm to find the shortest distances. How many of you have seen this algorithm? Fine. So we start with the algorithm. We initialize a set S. So the set basically consists of all elements whose distances from U have been finalized. Finalized in the sense that we are sure that the distance of that particular node from U is, we know it already. So at the beginning, we know that the distance of U from U is 0, hence S is equal to U. We'll keep on updating S and adding more nodes to it. When we have the complete set of vertices in S, then we are done. The next thing that we'll maintain is an array D, which denotes the shortest distance of each point from U only going through elements of S. So as in the figure, I have node U which is in S. So from U I need to go to say element I, only traveling through elements in S. In the beginning, we can see that when S is equal to U, I'll only contain all direct edges of U. Now, the shortest of the distance is D. I take it and I claim that this is certainly the distance between U and I. So, as I now show that this is the distance between U and I add I to S and I update D as well. Why would I need to update D? Okay, what's D? D is the distance between U to all the vertices, but there's one more thing in there. Via elements of S. So I've just changed S, I've added element I to S, hence my array D will change. What sort of changes would there be in D? Okay, so if the new shortest path will pass through the new node I, then D should change. So I can accordingly update it. The thing that we are now left with is to prove that the smallest value of Di is certainly the distance between U and I. So let's say I have a node U inside S, as we saw earlier. Its distance with I is Di, and I also have the remaining nodes, V minus S minus I. Now if I look at any path from U to I, there are two options. Either it just goes directly through S without passing through the remaining nodes. In that case, I know that the shorter distance is Di. There is a second possibility as well, that I first go through the remaining set of nodes and then I come back to it. I am aware that as di is the smallest value of in D, so if I move from U to any of the other remaining nodes, I'll need to cost greater than di. So the first transition from U to the remaining nodes via elements of S must have cost greater than di. And by my constraints of the problem, any edge would have positive cost, hence the second path would also have greater than zero cost. So if I look at this entire path, the cost would be greater than di. Is that clear? Is it? Right. So if I move directly, I'm getting cost di. If I'm indirectly going via the remaining nodes, then by my proposition of this being the minimum cost, I'm already charging cost greater than di. Hence, this must be my minimum value, minimum cost path. So we have a question now. We are given an unweighted graph. In addition to that, we also have some free transitions between nodes. So you can also move from one node to another with cost 0. So now again you need to find single source shortest path from any particular node. How could we do this? Has anyone seen such a problem before? Yeah. So, okay. The first thing is that we could convert this into a weighted graph so that the weights are only 0 out. The edges that are present in the original graph basically are weight 1, and the free transitions that we have weight 0. So because we have, okay, now we have a weighted graph with weights 0 and 1. My first question is, can we use Dijkstra's here?
It will be of more complexity.
Yeah, we can use it, right?
Yeah.
Fine. So we could use Dijkstra's algorithm as well, but as you said, that would take too long. We are not using the fact that the weights can only have value 0 or 1. We are assuming that the weights can have any value. Also, moving to the previous slide, I've written that this should be greater than 0, in this case this would be equal to 0, but that's not an issue. Fine, so we can use Dijkstra's, but that would be an overkill. And we can't use DFS because we even have some free transitions that we can't look at in DFS in its original form. So that's why we propose a slight variation of DFS called 0-1 DFS. And so we had the queue that we were maintaining while implementing DFS, right? So the purpose of that queue was basically to make sure if I'm currently at a node which is at distance I, then I need to add all nodes that are at distance I plus 1. So I maintain those nodes in a queue. So, right. So fine. So the queue that I was maintaining, if I am at a node currently, that's a distance I. All edges that I have from that node, I simply add those nodes to the back of the queue. If my current node is a distance I, the last nodes would be a distance I plus 1, and hence I just I process the nodes in order of increasing distance. Right. However, in this case, if I have an edge from a node, the new node could either be a distance I or it could be a distance I plus 1. Right. So, what should we do if the new node is a distance I? We could simply add it to the front of the queue, right? So, if the new node is a distance I add it to the front of the queue. If the new node is a distance I plus 1, I add it to the back of the queue. And again, I would only be processing nodes in order of increasing distance from the source node. So that's a minor tweak in BFS called 0-1 BFS, and we can use it for such scenarios. Fine, we have another question now. We have a weighted graph with n vertices and m edges. Consider two nodes u and v. You are allowed to make an edge between any two nodes x and y of given weight k. How many choices of x comma y are there such that the shortest distance between u and v will not decrease? You could take some time for this. Again, probably around 2 minutes. So k is greater than 0. Even if it's not greater than 0, I guess it won't make a difference.
एक्स एंड वाई का ये हो सकता है कि वो शॉर्टेस्ट पाथ में लाइक मतलब यू टू वी जाने वाला पाथ में एक्स एंड वाई इन दैट केस अगर एक्स एंड वाई का प्रेजेंट रेट से के कम है तो फिर आएंगे या फिर एक्स वाई जिन्हें पाथ में ना लेकर
Can we add only one edge?
Yes, we can only add one.
you are allowed to make an edge between any two
Could anyone come up with a solution? Sorry, we should apply Dijkstra's from you. Okay.
For every x comma y, then we can check if you say x shortest path and y says v shortest path plus k. If it is greater than the shortest distance, then we can keep it. Otherwise, we cannot.
Okay, but why did we have to reverse the edges while doing Dijkstra only? That's the only issue. Otherwise, you're almost correct.
We can do that.
Okay, so again, the most important thing is how do you approach the problem? We have been asked to find the number of choices of x comma y such that the shortest distance between u and v is unchanged. So we need to first find how would the shortest distance between u and v be affected if we add an edge. So in what cases can the shortest distance reduce? So anyone?
We join two vertices in the shortest path and k is less than the length you need.
Just this part. So yeah.
If we are joining into vertices in the shortest path that we have from u and the k value is less than the time we are taking from going to u v1 to u.
Okay, so that's one case. Yes. So what she said is. But let's say the shortest path from u to v looks something like this. If as of now this distance between any two nodes is k plus x, x greater than 0, so then if we add this edge of weight k, then clearly this would give us some reduction in the shortest path. So that's one case. But if we have to go by this algorithm, firstly, there could be multiple shortest paths. And then going through each pair of vertices seems rather difficult. So that's an implementation issue. But even except for that, this needn't cover all cases. Do you think that these two nodes need to be on the shortest path? Let's say this is the shortest path of weight, say 100. Let's have another path which is of weight 101. And let's say this distance is k plus 20. If instead of, if I even add one edge here, even then my new shortest path would be 101 minus 20, right, which is 81. So that's one subset of cases where we could benefit. Could anyone generalize all such cases?
d of ux plus d of uy plus k should be within.
So, okay, that's going slightly further ahead. So the main thing is that if we could involve the edge between x and y to get the new shortest path, in that case, we can benefit. So, yeah. If we are not using the edge x comma y to make the shortest path, then of course there's no difference in adding x comma y, right? So now the new shortest path must look something like this. We go from u to x, then xy is in edge, and then we move from y to v. It's clear to see what would be the length of such a path, right? So it's a distance between u and x as per the original graph plus distance xy, which is k, plus the distance between y and v. So now we can say that if this distance is less than the initial distance between u and v, then we are benefiting. And how could we find distance between u and x, distance between v and y? We could simply apply Dijkstra's with two different sources. So we apply Dijkstra's twice, we get all the values of dx, dvy. We iterate through all possible x and y in order n square time. We'll be able to figure out all possible pairs. Okay. Another question. We are given a graph representing n cities and m roads between them. Each road has certain length which represents the cost to travel across the road. There are n hospitals, one in each city. The ith hospital has some charge Ci. for a person in any city J, that is for all cities, find the minimum cost for him to reach a hospital. So we have a normal graph. In addition to that, each node has a hospital that charges a certain amount. A person needs to go from his particular hometown to a hospital in any city. And we need to find the minimum charge for him.
Here, we have to pay some cost to travel the road also and to get into the hospital.
Yes.
There are two costs.
Yeah. So it's a normal graph plus at each city, at each node, we have a hospital. To enter the hospital, we need to pay an extra fee.
ट्रैवल कॉस्ट का इनपुट क्या है?
क्या?
ट्रैवल कॉस्ट का इनपुट क्या है?
Normal graph है n nodes, m edges,
वेटेड एजेस हैं और
weighted edges.
नोड्स भी वेटेड है।
Nodes ऐसे weighted नहीं है, hospital का charge है.
तो वो एजेस का वेट जो है हॉस्पिटल का चार्ज है।
नहीं, अलग अलग quantities है. Normal graph with weighted edges plus a hospital in each city. The hospital charges some extra amount. So you need to first reach the city, then you need to pay some additional amount to go to the hospital.
Do we have to calculate for starting from only one city or all cities?
For all cities.
We can apply extra from the node J, and then for each vertex in the array D, we can add the corresponding hospital cost of that vertex.
So the first thing is that we need to do this for all nodes. For any node things for all nodes. Otherwise the answer is there. Like normal n square or n log or whatever. That depends on the value of n. So you'll be able to do it in n square if you're independent of any log. For a dense graph, you'll be able to do it in n square. Okay, so there's a small trick that we could use for this question.
V square.
If we look at the path of the person, he needs to first move from his city J, let's say, to the city or the hospital, whatever it is. And then you could say that within the city, then he needs to move from wherever he reached till the hospital in the city. Right, so and instead of assigning the cost to what the hospital will charge, I could instead say that's the charge to go from the city to the hospital inside the city. So could you now come up with something? I've just worded the question differently. The hospital doesn't charge me any amount, but moving from the city to the hospital charges an extra CA amount.
You can update each edge based. If there is edge from U to V, you can add the cost of that base load to that edge.
So that means that if I move from U to V, I must go to the hospital. So again, what I said is that instead of saying that the hospital charges any amount, the hospital is now free of cost, but I need to travel from the city to the hospital in the city. Sort of, yes. Yes. Yeah.
Is it necessary that if a person is going to a city, he will visit the hospital?
No, it's not necessary.
So he can go to another city from another.
Yes, yes. He'll only visit one hospital in the final city.
So it can happen that if I suppose that I am at a city 1 and I go to city 2, the length of the road is 1.
Yeah.
The hospital there costs 1 lakh rupees.
Yeah.
And there exists one another road which is also of length 1, but the hospital costs only 2 rupees there.
Yeah, so then you will take that.
So how is your scheme?
No, so I have just changed the costs. So all I'm saying is that I have another road from the city that goes to the hospital inside the city. And that road has cost C.
So there are 2 routes now.
Yeah, so basically from each city I've added one more road that goes to the hospital. One more edge. So let's say initially
इसका वेट को तू 0 कर दे और ये वेट को इधर रख दे।
so if initially this was my city,
जो भी तेरा
say
ये
this,
बात जो इधर आती है
and I had a hospital inside the city. To go inside I need to pay some cost, right? So I'm saying that I'm adding this here. That fine, I'm adding this as a different transition from here to here, and this has a certain cost. That's all. So if you look at my updated graph, that basically has 2 nodes and m plus n edges. Okay. If I try to apply Dijkstra's, let's see what I need to find in this graph. I need to find the shortest distance between any of the first n nodes to any of the second n nodes. Each of the second n nodes only have one edge connecting it to the previous one. So what if I club each of the hospitals into one? And instead of n hospitals, I only represent it as one node, and let me call it hospital node, and just say that to go from city I to the hospital, I need to spend CL. So I have added this common hospital node. This is my city 1 C1. This is say city 2. This is city 3. I've mixed up the notation, sorry for that. But and now I'm connecting nodes from each of the cities to the hospital.
इससे बेटर
And then I'm associating a cost with going from the city to the hospital.
so 2 and k
So would it be fine if I just find the cost from going to my particular starting node to the hospital? Fine, I just worded slightly better.
फर्क नहीं पड़ रहा
So, fine. So So instead of saying that I need to go from city I to hospital I, I'll just generalize that I need to go from city I to hospital. Because from my point of view, apart from the edge weights, all hospitals are identical. Right. So now I add one more node called the hospital, and to go from city I to the hospital, I need to spend CI. So that would basically be my basically be the weight of that particular edge. Now what do I need to find out? I need to find the shortest path from all nodes to the hospital. And that's basically a single source DAX class. Is it clear with everyone? Any issues? Might be slightly complicated, go ahead and ask. So I am creating an extra dummy node on my own to take care of whatever additions we have from the normal graph shortest single source shortest path problem. So this is clear, right? One more problem. You start at a point 1 in Guwahati. You have to reach the NH node before time t. There are m buses available scheduled from node UI to VI, starting at SI and reaching at EI. So each bus has a starting and ending point along with a starting and reaching time. You have to minimize the maximum waiting time at any node. So you don't need to minimize the distance traveled or the earliest to reach or anything like that. You need to minimize the maximum waiting time at any node, where the waiting time at a node is defined as the difference between when you reach that node and when you take the bus from that node. And you need to make sure that you reach in time, that is before time factor. So is that question clear to everyone? Question is clear, right? Not clear? So you are present at node 1. You need to go to node n. That's the first thing. Fine. Secondly, you need to reach them before time t. To go through nodes, you have a certain number of buses available. Each bus has a start time and end time, a starting destination and ending destination. So that's similar to edges with the added component of start and end times. And now you need to minimize the maximum waiting time at any node, where the waiting time is defined as the time you're spending waiting at the bus stop when you reach and before you board the bus.
This is not always possible.
It need not always be possible, yes.
So we have to.
Then you can tell that you won't be able to reach before time. Or we could make test cases such that it's always possible. Yeah.
I think if we take the conjugate of the full graph, that is now we construct a different graph where
What's
buses.
the graph? So
Initially we have the stops as the nodes and buses as the edges. But now we can take as buses as the node and distance and the time between we have to, like, if we have to stay at a node for 5 hours to get from bus I to bus A, then we'll call the buses as the nodes and an edge between them. Then we can do like the previous question.
okay.
Then again create one node that is the original starting node and apply distance from here.
Okay. So you have fine. And two buses are only connected if they have
One ending is the same as the other
same as the
starting.
other starting. And then to find the shortest paths. So
This will minimize the total waiting.
yes.
Not the time.
So you need a, I mean, then you need to minimize the maximum weight, which this is also a fairly good transformation, but you can't use that stance.
Not the next one.
Remember that even in graph theory questions, you'll also need to use other concepts. And this question in particular, it sort of combines one or two things, and then you get to the solution. Alright, so the first thing, let's say you can do this, let's say you can reach node n with a maximum waiting time of k. So would I be right to say that I can also reach node n in time with a maximum waiting time of less than k plus 1? So if I draw this number line, so this is 0. This number line basically represents the maximum waiting time, rather the minimum, yeah, so the maximum waiting time that's allowed. So if I can, so if with maximum waiting time k, I can reach node n in time, I can also reach there with maximum waiting time k plus 1, right? If I just take the same path, if the maximum waiting time is less than k, it's also less than k plus 1. Right, so so if this is my answer, then I can say that for anything to the left of this with a waiting time, let's say this is the waiting time. So if I'm only allowed a maximum waiting time of less than this, then I won't be able to reach node n in time t. If I'm allowed anything more than this, I'll be able to reach node n in time t, right? So it's this particular value k that I need to find. How could we do this?
Binary search.
Binary search, right? So that's the first thing, that we'll do binary search on the answer. Now, if we are in a particular iteration of binary search, what's the problem we are faced with? So initially, let's say we have some range. This is 0, this is say t. So what do we do in the first step? We find the mid value of these two, say somewhere here. Now I need to find out whether m is to this side of p or to this side of p. And in each iteration of binary search, that's essentially the only problem I'll be facing.
Can you define k again once?
So k is the answer to my problem. It's the minimum waiting time with which I can reach node n in time t, time less than t. Let's say that if I'm at a node, I'll only wait for say x seconds. So if I say that I'll only wait for say x seconds, the moment the waiting time crosses x, I'll assume that there's no bus here and I'll go off to sleep. Then, so then if I put x to k or to any value greater than k, then I'll be able to reach my destination. Right. So as I've shown here, in each iteration of binary search, I need to find out whether for a particular max waiting time of n, whether I will be able to reach node n in time t or not. That is, if the waiting time of w is sufficient or not. Right. Again, how could we go about this? We are short on time, so I guess I'll myself go through the algorithm. So we need to find out if a waiting time of w is sufficient to reach my final destination in given time. So if I'm at a particular node, I need to find, I need to do something similar to a DFS, and I need to figure out all the nodes that are reachable. Along with that, I also need to store the time at which I'll be reaching those nodes, because time is important in this problem. So my problem is to do something similar to a DFS and then store that I can reach this node at this time and so on. So if I start with node 0, the initial node, node 1, I can only take a bus if it starts up till time w. Any bus starting after w, I won't be able to take. At least initially, I won't be able to take. Right. And then I could accordingly update for the final destination that I'll be able to reach here in time, the reaching time of the bus. Right. If I keep on repeating this process in probably some organized manner, then I'll be able to find out whether I can reach node n in time t or not. So the only thing that we need to figure out is in what order or in what manner should we do this, form these steps, so that I'll be able to correctly figure out which all nodes are reachable. I don't want to miss any opportunity to go. So the only thing that I need to make sure is that if I'm considering a bus that starts from a node u at time t, then if I can, then all the buses that reach node u before time t, I should have already processed them, right? Because I want to know that if I can be present at u before time t, then I should have already stored that in whatever manner. Is this clear? Otherwise, okay, let's say I first process a bus. So let's say I first process a bus that, so this is my axis of time, and I first process a bus that starts here and it goes wherever. After that, I come to know that okay, it's also possible that I would have reached the same node at this time. Then of course I missed the fact that this guy reaching here, he could have taken this bus and then gone further. So that's why it's important that whenever I'm processing a bus, I completely know when all a person can reach before that bus starts. So that's why it makes sense that I process, instead of processing node by node, I process bus by bus, and I process them in increasing order of reach time. Right. So for each node, I am maintaining when all I can reach that node, and I'll maintain it in sorted order so that it's easy to process. Now I need to go through each bus. If a bus starts at time s, then if I can reach that node up till time s minus w, then I need to take that bus and update my list of reaching times that are called r. So basically, I need to update that I can now reach the destination of that bus at whatever given time. And yeah, if I just repeat this process for all buses, I'll be done. Few implementation things that if I need to know that, fine. So if I know that my bus, this is for a particular node U. If I know that my bus reaches at this time, and now I need to find out all entries that are up till d minus w, I could do that through binary search because I have this as a sorted list. So I'll find all nodes that are in this area, I'll make them take this bus, and then I'll accordingly update that I can reach the destination of this bus at whatever reaching time it is. And if I keep iteratively, if I keep doing this for all buses, I'll know that after taking these set of buses, I could what's the earliest time I could reach node any particular, what are all the different times I could reach any node. So the main thing was binary search, and after that it's important that you know that you are supposed to process it bus by bus in increasing order of reach times. Is this clear? Was it not clear to you? You could ask me if it's not clear, it's okay. Fine. So, right from the start of the slide? Fine. So, I'm processing bus by bus in order of increasing reach times. So, the bus that reaches any node first will be processed first. Okay. Now, I'm maintaining a list. Let's say it would be something like a 2D vector. If you are acquainted with what are vectors. So let's say I have a 2D vector R. Right, and Ri denotes when all I can reach node I. So this will look something like this. So I can reach node I at each of these different times. Fine. Now I'm processing the bus B. B starts at time S and starts from U, or okay, let's say, fine, this is U, starts from SU and it reaches at E comma B. Fine. Now I need to see if in this list I have an entry after S minus W. I could do that through binary search. Would I even need binary? I think if I just look at the I need binary search. Looking at the back of the vector might not suffice. Fine. So through binary search, I'll find if this particular thing has any entries in the range S minus W to S. If there is even one entry, then I will update R P and I will add E to it. So this is RE, then I will add this particular entry. In this manner, if I keep processing each bus, I will know what all nodes I can reach at what different times I can reach them. After I'm done with processing each bus, I'll check if I can reach node n before time t and I'll accordingly answer my query. That's fine? Fine with everyone? Fine. One last thing to finish off. The lowest common ancestor of a tree. So this is a fairly advanced algorithm. It's not difficult to understand as such, but uh, you could call it in the advanced section of trees and graphs. So firstly, I'll define what's the lowest common ancestor. How many of you have seen this algorithm before? Alright. So the lowest common ancestor is, I'll firstly define an ancestor. So any parent, grandparent, or anyone that comes in the path of the node till its root is an ancestor of the node. The lowest common ancestor is the one that comes first going bottom up. Alright, so for these particular nodes 4 and 7, 2 is its lowest common ancestor. Right. So we have an algorithm to find the lowest common ancestor of a query in log n time. So, fine. There are some pre-computations required for this algorithm. The first, fine. So we perform DFS on the tree, and during the DFS we need to compute certain things. The first thing is that we'll keep an array. For each node we'll keep an array. So if my array is, fine, I defined it there as well. If my array is ANK, so then ANK I is basically the 2 power ith ancestor. So basically, instead of storing each of its ancestors, I've stored ancestors at different intervals. If I need to store this, I could simply do this during the DFS because I have a recursive relation. The ith ancestor of V, rather the 2 power ith ancestor of V, is equal to the 2 power. So if I need to go 2 power I up from V, I first go 2 power I minus 1 up from V, and then I go further 2 power I minus 1 up from that node. So recursively, I can calculate it in order n time, this entire arithmetic. Sorry, not order n time, the number of entries in the array. There's another thing I need to calculate, which is the T in and T out times of each node. I haven't explicitly told you what's meant by T in and T out. So I'll go back to the, okay, I'll take it. So let's say we have a particular tree here. So whenever I do DFS, I would first reach this node, then I would say go to this node, I'll perform DFS here, then I'll come back, then I'll do for these nodes, then I'll again come back, and then I'll move to its parent. So the first time when I enter this node, that is the end time of this node. So I enter this node, then I go here, here, here. The moment I enter this node, I call it T in. And similarly, when I'm done processing each of these and I'm moving out, then that time is called T out. So I can calculate this T in and T out times as well. It's clear to see that if a node is an ancestor of the other, in this case E is an ancestor of 1, so I'll first enter into Tn, then I'll enter into 1, Tn of 1, then I'll exit from 1, and then I'll exit from A. So clearly the Tn and T out times of 1 are sandwiched in between the Tn and T out times of A. So that's the relation I have for a node being the ancestor of another. So in order one time I can now calculate if a particular node is an ancestor of the other or not. And I also have the 2 power ith ancestor of each node. So now we need to handle least common ancestor queries. So if I am asked to find the least common ancestor of two nodes U and V, uh, so I would, yeah, firstly I just check if U itself is an ancestor of V or not, vice versa if V is an ancestor of U, and then after that I would start checking the 2 power ith ancestors of U and see if they are also an ancestor of U. So I am sort of now doing binary search on my array of ancestors, and I am trying to find the first ancestor of U, which is also an ancestor of V. And because I have only used powers of 2 in my ancestor array, it's effectively similar to a binary search. Alright? Now the first time I find, so like in this example, the first time I find I plus 1 is a common ancestor of both. So I would instead take the ith ancestor U comma I, and now again I would continue binary search from that node. I would continue going through the ancestors of ancestor U comma I. Okay. Now one thing we need to see is that if I've already covered I ancestors from U, I've gone through the ith ancestor. If I look at the ith ancestor of this particular node, ancestor U comma I, then that's basically ancestor U comma I plus 1, right? Yeah, so it's not very clear over there, but if this is U, this is the 2 power ith ancestor of U, and this is another further 2 power I up from this guy. So I've seen that this guy is above the LCM, right? So now I'm placed here. If I look at the 2 power I guy from here, I know this guy is also above the LCM because they are both the same. So I just need to start looking from the 2 power I minus 1 guy from here. So this is just to prove that if I'm looking at powers of 2, I can just linearly keep decrementing I irrespective of what the node is. So, so I just need to check for values of I from 1 to L, or n to 1 rather. Fine, and if I just keep repeating this algorithm, it's easy to see that each step we are moving closer and closer to the LCM, and we can also show that at the end of the algorithm, we would actually be converging at the LCM. Alright. So, I will just show this intuitive emailing. Okay, so one thing we know that we are always below the LCM. So if I look at my final node, again I will be below the LCM, and I would have just checked the parent of the node. And I'm aware, so okay, let's say I'm at I equals to 1 now. If I'm at I equals to 1, it means that I know that the 2 power second ancestor is above the LCM. Right, that's why I'm only checking for the second ancestor. So, and in particular, if I choose I equal to 0, then I know that until I minus 1, I'm crossing or reaching the LCM. Okay, I'm only crossing the LCM, which basically means that either the parent or that particular node, or basically means that the parent must be the LCM, right? Because I'm aware that 2 power 1 crosses the LCM. Currently I'm below the LCM, so 2 power 0, that is the 1th parent, the direct parent must actually be the LCM. Yeah.
When we write check if U is ancestor of V or vice versa, do we just mean if U is in the ancestor array of V and V is in the
No, ancestor. So we have the TN and T out times, right?
Yes.
So with that we can check if it is directly above. Alright, that's it from my side. There are a lot of topics that I haven't covered, but the main purpose of this session was, firstly, if you're starting off, to give you a good background with which you can start learning graph theory. And if you had already started graph theory, then maybe you could. Then I think the questions that I discussed would sort of give you good insights into how you could approach problems, apart from obviously even telling you some particular types of ways that you could use to solve those problems. A lot of basic topics were not covered, but you're probably in a position to go and learn this as well. Learn that. Okay, thank you.
Guys, tomorrow there will be a lecture on segment trees, so you come for that. And also, if there were any first year guys here, anyone from first year? So if you guys have difficulty in understanding, then you can also first of all do the CP.begin course. So you got some basic concepts there, so that can be done.